There is something about physics that has been really bothering me since I was a little kid. And it's related to a question that scientists have been asking for almost 100 years with no answer. How do the smallest things in nature, the particles of the quantum world, match up with the largest things in nature, planets and stars and galaxies held together by gravity? As a kid, I would puzzle over questions just like this. I would fiddle around with microscopes and electromagnets, and I would read about the forces of the small and about quantum mechanics, and I would marvel at how well that description matched up to our observation. And then I would look at the stars, and I would read about how well we understand gravity, and I would think, surely there must be some elegant way that these two systems match up. But there's not. And the books would say, yeah, we understand a lot about these two realms separately, but when we try to link them mathematically, everything breaks. And for 100 years, none of our ideas as to how to solve this basically physics disaster has ever been supported by evidence. And to little old me, little curious, skeptical James, this was a supremely unsatisfying answer. So I'm still a skeptical little kid. Well, so flash forward now to December of 2015, when I found myself smack in the middle of the physics world being flipped on its head. It all started when we at CERN saw something intriguing in our data, a hint of a new particle, an inkling of a possibly extraordinary answer to this question. So I'm still a skeptical little kid, I think, but I'm also now a particle hunter. I am a physicist at CERN's Large Hadron Collider, the largest science experiment ever mounted. It's a 27-kilometer tunnel on the border of France and Switzerland, buried 100 meters underground. And in this tunnel, we use superconducting magnets colder than outer space to accelerate protons to almost the speed of light and slam them into each other millions of times per second, collecting the debris of these collisions to search for new, undiscovered fundamental particles. Its design and construction took decades of work by thousands of physicists from around the globe, and in the summer of 2015, we had been working tirelessly to switch on the LHC at the highest energy that humans have ever used in a collider experiment. Now, higher energy is important because for particles there is an equivalence between energy and particle mass, and mass is just a number put there by nature. To discover new particles, we need to reach these bigger numbers. And to do that, we have to build a bigger, higher energy collider, and the biggest, highest energy collider in the world is the Large Hadron Collider. And then we collide protons quadrillions of times, and we collect this data very slowly over months and months. And then new particles might show up in our data as bumps, slight deviations from what you expect, little clusters of data points that make a smooth line not so smooth. For example, this bump, after months of data taking in 2012, led to the discovery of the Higgs particle, the Higgs boson, and to a Nobel Prize for the confirmation of its existence. And this jump up in energy in 2015 represented the best chance that we as a species had ever had of discovering new particles, new answers to these long-standing questions, because it was almost twice as much energy as we used when we discovered the Higgs boson. Many of my colleagues had been working their entire careers for this moment, and frankly, to little curious me, this was the moment I'd been waiting for my entire life. So 2015 was go time. So June 2015, my colleagues and I, the LHC is switched back on. My colleagues and I held our breath and bit our fingernails, and then finally we saw the first proton collisions at this highest energy ever. Applause, champagne, celebration. This was a milestone for science, and we had no idea what we would find in this brand new data. And then a few weeks later, we found a bump. It wasn't a very big bump, but it was big enough to make you raise your eyebrow. But on a scale of 1 to 10 for eyebrow raises, if 10 indicates that you've discovered a new particle, this eyebrow raise is about a 4. I spent hours days, weeks in secret meetings arguing with my colleagues over this little bump, poking and prodding it with our most ruthless experimental sticks to see if it would withstand scrutiny. But even after months of working feverishly, sleeping in our offices and not going home, candy bars for dinner, coffee by the bucketful. Physicists are machines for turning coffee into diagrams. This little bump would not go away. So, after a few months, we presented our little bump to the world with a very clear message. This little bump is interesting, but it's not definitive. So, let's keep an eye on it as we take more data. And so we were trying to be extremely cool about it. And the world ran with it anyway. The news loved it. People said it reminded them of the little bump that was shown on the way toward the Higgs boson discovery. Better than that, my theorist colleagues, I love my theorist colleagues. My theorist colleagues wrote 500 papers about this little bump. The world of particle physics had been flipped on its head. But what was it about this particular bump that caused thousands of physicists to collectively lose their cool? This little bump was unique. This little bump indicated that we were seeing an unexpectedly large number of collisions whose debris consisted of only 2 photons, 2 particles of light, and that's rare. Particle collisions are not like automobile collisions. They have different rules. When 2 particles collide at almost the speed of light, the quantum world takes over. And in the quantum world, these 2 particles can briefly create a new particle that lives for a tiny fraction of a second before splitting into other particles that hit our detector. Imagine a car collision where the 2 cars vanish upon impact, a bicycle appears in their place, and then that bicycle explodes into 2 skateboards which hit our detector. Hopefully not literally. They're very expensive. The events where only 2 photons hit our detector are very rare. And because of the special quantum properties of photons, there's a very small number of possible new particles, these mythical bicycles, that can give birth to only 2 photons. But one of these options is huge. And it has to do with that long-standing question that bothered me as a tiny little kid about gravity. So, gravity may seem super strong to you, but it's actually crazily weak compared to the other forces of nature. I mean, I can briefly beat gravity when I jump, but I can't pick a proton out of my hand. The strength of gravity, compared to the other forces of nature, is 10 to the minus 39. That's a decimal with 39 zeros after it. Worse than that, all of the other known forces of nature are perfectly described by this thing we call the Standard Model, which is our current best description of nature at its smallest scales, and quite frankly, one of the most successful achievements of humankind. Except for gravity, which is absent from the Standard Model. It's crazy. It's almost as though most of gravity has gone missing. We feel a little bit of it, but where's the rest of it? No one knows. But one theoretical explanation proposes a wild solution. You and I, even you in the back, we live in 3 dimensions of space. I hope that's a non-controversial statement. All of the known particles also live in 3 dimensions of space. In fact, a particle is just another name for an excitation in a 3-dimensional field, a localized wobbling in space. More importantly, all the math that we use to describe all this stuff assumes that there are only 3 dimensions of space. But math is math, and we can play around with our math however we want. And people have been playing around with extra dimensions of space for a very long time, but it's always been an abstract mathematical concept. I mean, just look around you at the back, look around. There's clearly only 3 dimensions of space. But what if that's not true? What if the missing gravity is leaking into an extra spatial dimension that's invisible to you and I? What if gravity is just as strong as the other forces if you were to view it in this extra spatial dimension, and what you and I experience is a tiny slice of gravity, make it seem very weak? If this were true, we would have to expand our standard model of particles to include an extra particle, a hyperdimensional particle of gravity, a special graviton that lives in extra spatial dimensions. And I see the looks on your face. You should be asking me the question, how in the world are we going to test this crazy science fiction idea stuck as we are in 3 dimensions the way we always do, by slamming together 2 protons hard enough that the collision reverberates into any extra spatial dimensions that might be there, momentarily creating this hyperdimensional graviton that then snaps back into the 3 dimensions of the LHC and spits off 2 photons, 2 particles of light. And this hypothetical extra-dimensional graviton is one of the only possible hypothetical new particles that has the special quantum properties that could give birth to our little 2-photon bump. So, the possibility of explaining the mysteries of gravity and of discovering extra dimensions of space, perhaps now you get a sense as to why thousands of physics geeks collectively lost their cool over our little 2-photon bump. A discovery of this type would rewrite the textbooks. But remember, the message from us experimentalists that actually were doing this work at the time was very clear. We need more data. With more data, the little bump will either turn into a nice, crisp Nobel Prize, or the extra data will fill in the space around the bump and turn it into a nice, smooth line. So we took more data, and with 5 times the data, several months later, our little bump turned into a smooth line. The news reported out a huge disappointment on faded hopes and on particle physicists being sad. And given the tone of the coverage, you'd think that we had decided to shut down the LHC and go home. But that's not what we did. But why not? I mean, if I didn't discover a particle, and I didn't, if I didn't discover a particle, why am I here talking to you? Why didn't I just hang my head in shame and go home? Particle physicists are explorers, and very much of what we do is cartography. Let me put it this way. Forget about the LHC for a second. Imagine you are a space explorer, arriving at a distant planet searching for aliens. What is your first task? To immediately orbit the planet, land, take a quick look around for any big, obvious signs of life, and report back to home base. That's the stage we're at now. We took a first look at the LHC for any new, big, obvious-to-spot particles, and we can report that there are none. We saw a weird-looking alien bump on a distant mountain, but once we got closer, we saw it was a rock. But then what do? Do we just give up and fly away? Absolutely not. We would be terrible scientists if we did. No, we spend the next couple of decades exploring, mapping out the territory, sifting through the sand with a fine instrument, peeking under every stone, drilling under the surface. New particles can either show up immediately as big, obvious-to-spot bumps, or they can only reveal themselves after years of data taking. Humanity has just begun its exploration of the LHC at this big high energy, and we have much searching to do. But what if even after 10 or 20 years, we still find no new particles? We build a bigger machine. We search at higher energies. Planning is already underway for a 100-kilometer tunnel that will collide particles at 10 times the energy of the LHC. We don't decide where nature places new particles. We only decide to keep exploring. But what if, even after a 100-kilometer tunnel, or a 500-kilometer tunnel, or a 10,000-kilometer collider floating in space between the Earth and the Moon, we still find no new particles? Then perhaps we're doing particle physics wrong. Perhaps we need to rethink things. Maybe we need more resources, technology, expertise than what we currently have. We already use artificial intelligence and machine learning techniques in parts of the LHC, but imagine designing a particle physics experiment using such sophisticated algorithms that it could teach itself to discover a hyperdimensional graviton. But what if the ultimate question, what if even artificial intelligence can't help us answer our questions? What if these open questions for centuries are destined to be unanswered for the foreseeable future? What if the stuff that's bothered me since I was a little kid is destined to be unanswered in my lifetime? Then that will be even more fascinating. We will be forced to think in completely new ways. We'll have to go back to our assumptions and determine if there's a flaw somewhere. And we'll need to encourage more people to join us in studying science, since we need fresh eyes on these century-old problems. I don't have the answers, and I'm still searching for them. But someone, maybe she's in school right now, maybe she's not even born yet, could eventually guide us to see physics in a completely new way, and to point out that perhaps we're just asking the wrong questions, which would not be the end of physics, but a novel beginning. Thank you.